In this video, we're going to look at the different types of plate boundaries on Earth. So the first plate boundary is called a divergent plate boundary, and I like to think about this poem by Robert Frost. You've probably heard it. Two roads diverged in a wood, and I took the one less traveled by, and that has made all the difference. And so I put this on here because it uses the term diverged, which is a great time to really think about what that means. In this case, that means the path split into two, like you see here in this yellowed wood. And so they split and the paths move away from each other. So what that means is in a divergent plate boundary, the plates are moving away from each other. Now, divergent plate boundaries begins with a continent. So we start with just a nice solid piece of granite lithosphere, a little bit of granite crust there, and it starts pulling apart. And this is a series, a series of steps that happen here. So it pulls a little bit, you get a little rift. It pulls a little bit more, you get this big wide rift valley, and you can see the volcanoes in there. And eventually, what happens is it pulls it so far apart that those pieces of the crust, that granite, don't touch anymore. And when they don't touch, it's not like you can have just mantle sitting there. So what happens is those volcanoes that were forming in the Rift Valley start filling that in, and you get oceanic crust. So while divergent plate boundaries start on a continent, they end up ending in an ocean. Now this begs the question though, why is the mantle melting here? Well, I guess part of it is, why doesn't the mantle melt in the first place? It's really hot, right? So it's pressure. Pressure keeps that mantle solid. And that pressure is called lithospheric pressure. It's the weight of the rocks above it pushing down on it. But when you start pulling things, if you ever done a taffy pull, you pull and pull and pull and it gets thinner and thinner and thinner, or even pizza crust, right? The thinner you pull your pizza, the thinner the crust gets. In this case, it's pulled and pulled and pulled until it's really, really thin. And that means there's less weight pushing down. And when there's less weight pushing down, there's less pressure. And so this melting is caused by what we know as decompression melting. As you lose pressure on it, the temperature now is high enough to be able to melt those rocks. And you get volcanoes. So you get volcanoes along these divergent plate boundaries. It makes them very easy to remember. You're also going to get earthquakes, because if you look in the picture here, those are a lot of faults. And faults just a break in the rock where you have movement, but there's lots of room for those to move around, which means you get lots of earthquakes. Now notice though, it's going to be just in that crust. So these earthquakes aren't very deep inside the earth. Now here's some beautiful examples of these continental rifts. So it's those big rift valleys that have formed. One of my favorites is the Basin and Range province. Now you actually happen to live in the Basin and Range here in the Phoenix Valley. So the Basin Range covers most of Nevada, a little bit of Southern California, a little bit of Southern Arizona, a little bit of Utah. And it's called Basin and Range because you have these mountain ranges separated by big valleys or basins, and that's exactly what Phoenix looks like. So that's why we have these mountains around us in this big flat valley in the middle. When we talk about geologic structures and faults, we're going to look at these a little bit closer. Right down in the bottom here, this is actually Death Valley. And if you've never been there, you might be surprised at just how much topography there is. This is actually a picture looking down from Telescope Peak. It's the highest peak right outside of Death Valley. It actually gets snow during the winter, so it's actually really tall. But you can look down and see those salt flats down in that nice low valley. So that's always, these big valleys are a good indication of divergent plate boundaries. So another example that you'll hear is this lovely East African Rift. So the East African Rift Valley is shown here in the yellow. So there's a couple different segments of it. What's happening is this whole eastern part of Africa is actually pulling, and that's happening at the same time as the Arabian Peninsula is being pulled away from Africa too, and that's what's causing the Red Sea. This is that next step in the process. So you can see all of this Africa is kind of turning kind of clockwise here. So once that continental rift gets wide enough and you start filling it in with basalt and you get that oceanic crust, you get a narrow seaway, and a great example of that is the Red Sea here. So this is just a little bit more advanced. And you can sort of see the topography down. There's actually a little ridge of volcanoes running down the middle of it. So there are volcanoes that are erupting on the bottom of the Red Sea. Now that ridge down the middle is how the oceans grow. So if you want to recognize a divergent plate boundary in the ocean, you're going to look for these big ridges. So it's a positive feature. They stand out above the ocean floor. Some famous ones are the Mid-Atlantic Ridge, and we've looked at that. I think I pointed that out in the last video, and the East Pacific Rise, although there's quite a few of them in the ocean floor as well. But this is where seafloor spreading is happening. You can see with the mantles melting, thanks to decompression melting, that new material moves up, pushes that older crust out of the way, then new material comes up and pushes that out of the way. And so little by little, by adding just little bits to that mid-ocean ridge, that's how the entire oceans grow. And so this right here is what actually broke up Pangaea. You started off with a continental rift, then you got a big rift valley, then you had a narrow seaway, and now it's still opening up even further. So we look at those ridges worldwide. You can see there's a ridge here pretty much completely circling Antarctica. Right down smack through the middle of the Atlantic Ocean is the Mid-Atlantic Ridge. Over here in the Pacific is the East Pacific Rise, and you can see that young rock is spread out pretty far versus over here in the Atlantic where it doesn't spread, or even this little segment here south of Africa. So you can see they look a little bit different. When we talk about oceans, we'll actually look a little closer at these. So if we want to compare those, you have these ridges that stand up high off the ocean floor. You have these really nice rift valleys down the middle that you can see on the ridge. This is a good indication that your ridge is spreading really slowly. Versus some of these locations where you can't see that rift valley. It's kind of a bulge. And the reason is that hot material, that hot young material, is still pretty kind of bouncy and low density. And as it cools further, it becomes more and more dense and collapses down. So that really young stuff right here is what's keeping it from forming a valley. And that's a fast spreading center. So you got really hot material still pretty far away from that ridge center. Now these are not great pictures. I'll show you some better ones here, but you can actually see it even on the map. This is a picture from the map that's hanging on the wall in the classroom. But you can see right down the middle of that Mid-Atlantic Ridge is that valley. Versus over here in the East Pacific Rise, you're missing that valley. There's another shot at those, and it shows up even better here in the Mid-Atlantic Ridge. So what this means is that the Mid-Atlantic Ridge is spreading much slower than the East Pacific Rise. So those oceanic ridges account for most of the divergent plate boundaries on Earth. And remember, since that's spreading and creating new volcanic material, those are basically really, really long volcanoes. Now, if you want to make sure you know what a divergent plate boundary looks like, you look for volcanoes. On the left is a picture of Ubi Hibi crater. That's one of the volcanoes actually in Death Valley. It's pretty young, and it may sound surprising, but there are quite a few volcanoes through Death Valley. We even have them here around us here in this part of Arizona. On the right is Erta Ale in Ethiopia. So that's a major lava lake right along the East African Rift Valley. You're also going to look for small, shallow earthquakes. Now here's a map of all the earthquakes through the basin and range between 1872 and 2009. At least the big ones. Because notice these are all the ones over a magnitude 4. Most of them are in the 4 to 5.9 range, so not very big. Some of these have been pretty dangerous. Like the Lone Pine earthquake was deadly, and that happened in Lone Pine, California, right along the base of the Sierra Nevadas. But you can see there's quite a few of those there. And of course, it's that Rift Valley. And in the case of basin range, you get fairly low elevations. There's places that it gets really low, like Death Valley. In Death Valley, if you look right here, you can see sea level way up here. And all the people way down here. It's actually kind of overwhelming to stand down there and see that. So it's over 200 feet below sea level here. And all that is indicative of the crust being really thin. So remember, these are places where that granite of the continental crust can get down to 20 kilometers thick even. Now we take a little foray into convergent plate boundaries, and how I like to remember this is if you think of a convention, like Comic-Con, those are places where lots and lots of people come together. So in a convergent plate boundary, you have plates moving towards each other. The most important part here is what type of crust is involved. Because if you remember, there's two main types of crust. You have the thin oceanic crust made of basalt, and you've got thick continental crust made of granite. So what that means is there's different types of convergent plate boundaries. You can have a continental convergent plate boundary. These are often called continental collisions. And that's where you have two big chunks of granites that are running into each other. You can have two sheets of oceanic crust moving together. You see those are nice and dark, just like basalt is. Or you can get one of each, a continental and an oceanic plate moving into each other. Now these all look a little bit different. Some of them look really different than the rest. So we're going to look at those in just a little bit more detail. If we start with ocean continental convergence, what happens is because the continental material is nice and thick and buoyant, but the oceanic crust tends to be a little bit denser and it tends to be quite a bit thinner. As this gets pushed together, the oceanic crust actually dives down under the continental lithosphere. So you can see in the picture where it's actually been pushed under. And there's actually pieces of the oceanic crust down deep inside the mantle. This is a process called subduction. And that's going to happen whenever you have oceanic crust running into something. The oceanic crust ducts. If that helps you remember, is it subducting? So as the oceanic crust dives under, it's full of water and carbon dioxide. And as it heats up, minerals start to break up and release even more of that. What happens is that material being released in the mantle actually lowers the melting temperature. Sort of like when you put salt on ice to help melt the ice on like roadways or sidewalks. It tends to lower the freezing point. So in this case, we're actually going to lower the temperature this rock needs to be to start melting. So you get melting in the mantle. Hot material rises. As it rises up, when it breaks through the crust, you get volcanoes. Now these volcanoes look a whole lot different than the ones on a divergent plate boundaries. Divergent plate boundaries tend to be pretty gentle. These here are pretty darn scary. And part of it is because it's mixing in with that material in the crust. And we're going to talk, when we talk about igneous compositions and when we talk about volcanoes, we'll talk a whole lot more about why that happens. Now one other thing I want to point out is this trench. This is how you can recognize a subduction zone in the ocean. So you always know it's a convergent plate boundary in the ocean if you have this trench. So it goes down versus, say, the mid-ocean ridge, which tells you that they're moving apart, which goes up above the surface. Now when you have two oceanic plates moving together, basically the same thing happens. That oceanic crust subducts. In this case, it's going to be the older and the colder oceanic crust that's going to duck under. The exact same thing happens. You get melting of the mantle. That moves up. It erupts on the surface. These are also pretty scary volcanoes, although they don't have as much of that granite to move through. Now, in this case, what you're going to have is a chain of volcanoes in the ocean. So you have a volcanic island chain. It's called a volcanic island arc. The key to this is all of those volcanoes are currently active, and they all potentially active at least. And this is going to be really different from another type of island chain we're going to look at in a sec. Notice here, there's also a trench, and really this trench is here because you can see as it goes down, you've got little flexure of both of those plates, and that makes it really deep. The deepest part of the ocean is at one of these ocean convergent plate boundaries in the Marianas Trench. The Challenger Deep is over 36,000 feet deep. Now, of course, if we're going to move to that continent-continent collision, where two pieces of continent run together. In this case, big things happen. This is how you get mountains. So the Himalayas formed when India, as it broke off of Pangaea, ended up colliding with Eurasia. And you can see in the diagram, it moved surprisingly fast, and it's actually still moving, so the Himalayas are still growing. So you get big mountain belt chains here. But I want you to notice when India was out here, between India and Eurasia was ocean. So what happens is you actually start with the subduction zone. So the oceanic plates are what move around. They either get pushed away from each other at divergent plate boundaries, or they get tugged towards each other, and you end up with these beautiful subduction zones, which drags them along with them. The continents are sort of just riding passively. So as that subduction zone is being dragged underneath this continent here on the right, this little piece of continental material on the left is just being tugged along. So eventually what's going to happen is these two are going to run into each other because of this. So continental convergence actually starts with an ocean and subduction. So you can see this is how that ocean ends up being closed up. So once they cram together, this is where we get that continent collision. You have mountain belts. And what happens here is that crust gets really thick. That's why the mountains are so tall, is because the crust thickens. Now, we've looked at two ways to cause melting. One of the ways was to thin the crust and cause decompression, like you get at divergent plate boundaries. In this case, you're actually increasing the pressure because there's even more weight. The other way is to add material into the mantle and make it melt, and that's what's happening over in this first section in a subduction zone. But by the time that the continents actually run into each other, nothing's going into the mantle. Usually the continents are kind of stubborn and neither one of them want to dive down under the... So in this case, you're not actually introducing anything into the mantle to cause it to melt. So a continent convergence has no volcanoes, which kind of sets it apart from the rest of it. Although you do get earthquakes, and lots of fairly shallow earthquakes, since it's mostly a crustal event. Our last type of transform plate boundary happens when two plates rub up against each other. Where this happens most commonly is actually along divergent plate boundaries. So here you see a spreading center. So there's a mid-ocean ridge. The Pacific plate is moving left. The Mendocino fault is moving right. But here's another chunk of it, and you can see it's offset. These aren't straight lines. They're actually offset in little chunks. So where those little chunks are offset, they rub up against each other. And I know that sounds like the lamest single example ever. But there are places on Earth that this happens on land. One of them you've probably actually heard of already. The San Andreas Fault is actually a transform plate boundary where the Pacific plate is moving sort of northwest and the North American plate is moving sort of southeast. And they rub up against each other. Now this is kind of a cool shot of the western part of the US because you can actually see all the different types of boundaries. Just off the coast where the Juan de Fuca plate meets the Pacific Ocean, there's a divergent plate boundary. But the Juan de Fuca plate is also diving under North America, and this is what's called the Cascade Subduction Zone. So this Cascadia region, you have the Juan de Fuca plate diving under, and it's causing volcanoes, and that's what causes all those cascade volcanoes like Mount Hood, Mount Baker, Mount St. Helens, Mount Shasta that we know. But you notice down here in LA, there's no volcanoes, and it's because transform plate boundaries, since the plates are just rubbing up against each other, you're not decreasing the pressure to get decompression and melting, and you're not introducing anything into the mantle to cause the volatiles to melt it. So you get lots of earthquakes, fairly shallow ones because it is still just pieces of the crustal material happening. But in this case, no volcanoes, just earthquake. Another pretty common one that you probably heard of is this one here on the right, is the northern edge of the Caribbean plate. So the right through here actually goes through the city of Port-au-Prince, Haiti. And the Haitian earthquake that happened in 2010 is thanks to this transform plate boundary. Now, we've probably all heard that California is going to have the big one. And when that happens, it's going to go sliding off into the ocean. But not quite. So what I want to do is I want to play a little video for you that shows you actually what's happened to California over history. So if we look here, this is 35, 36 million years ago. There's the Pacific Plate, here is North America, but between them was the Farallon Plate. Now this isn't even here anymore. But in this case, the Farallon Plate is being subducted under North America, and you have a spreading ridge between it and the Pacific Plate. So this is just like what you see in the Juan de Fuca Plate. So California is over here. Since there's subduction zone, that means you have volcanoes all the way down there. It also means you get really big earthquakes. Subduction zones are the big places to get really big, really deep earthquakes. But it's being subducted faster than it's spreading. And you can see that spreading center actually ends up being subducted under. And now the stresses change and it starts pulling. And that is how we have the San Andreas Fault System like it is. It's also how everything is spread out. And you saw all that tugging and pulling. That's what caused the basin and range. So you actually had a divergent plate boundary underneath the crust, which is quite bizarre. And you can see now that's how the Gulf of California opened up. Is that tugging and pulling was the Pacific Plate moves north. So what's happening is slowly this is opening up. So you're going to end up with a little sliver of Baja California, and part of Southern California is actually going to completely detach. And you'll have a long island off the coast of like northern and central California. So eventually LA is going to be on an island just off the coast of San Francisco. So it's not going to just slide off, even though we might hope for that sometimes. Now, intraplate regions can get exciting too. So plate boundaries aren't the only place things happen. So these areas in the middle of the plates are called hot spots. Now, hot spots are caused because you have hot material rising up from the core mantle boundary. It's so hot that it actually melts through the crust and it forms volcanoes. Notice this hot spot stays completely stationary as the plate moves across it. And so as the plate moves, it's going to drag those older volcanoes away. Then you have a new volcano and a new island. In this case, this is in the ocean, so a new island, and it gets drug away. And then you get a new one, and that old one gets drug away. So basically what you end up with is a chain of, at least in the ocean, it's a chain of volcanic islands, the youngest of which is the only one that's active. The older ones aren't active at all anymore. So that makes it fairly easy to recognize the difference between a hot spot and a volcanic island arc on a subduction zone. Now, there's lots of hot spots all over the world, but there's a few that are really well known. The Hawaiian chain is the big one. And the hot spot is under the big island of Hawaii, and it stretches out, and if we go to the other side, it connects onto the Emperor Seamount. And this has been active for about 65 million years. This one up in Iceland and this one down here, these are the two hotspots that actually probably broke apart Pangea. Because you can see this track of goes from either side of the Atlantic Ocean. Then everybody's favorite supervolcano, Yellowstone. Now this one isn't in the ocean, but there is a hotspot track that goes from the Columbia River basalts of eastern Washington down through the Snake River Plain, through Craters of the Moon in Idaho, and then finally Yellowstone National Park, where it is now. Now we can measure how fast these plates are moving even now. If you look, there's a map of the relative velocities. You can see, we've already mentioned this, that Mid-Atlantic Ridge is actually opening up pretty slowly versus the East Pacific Rise. So it's diverging at about 15.6 centimeters a year. Versus over here, even up kind of near Iceland, you've got close to 1.8 centimeters a year. You can see the Pacific Plate moves really fast and most of the plates around it. That's one of the reasons why that ring of fire is so active. So the ring of fire is this line all the way around the Pacific, if we keep over here. But you notice those are all subduction zones. That's what those little teeth mean. We can look at those Hawaiian Islands again. So we know where Hawaii is. That's the youngest material. So we know that it's erupting now, and the further you go to the northwest, the older it gets. And you can just use how far apart they are to determine an average rate of movement. We can also use some technology. So GPS systems you probably have even on your cell phone, and that's what helps you figure out how to get around. Your cell phone has decent range. It'll get you within a few hundred feet of where it thinks you are. But there are some GPS units that are actually so precise that it can measure the difference of just a couple of centimeters of motion on the Earth's surface, or of different locations on the Earth's surface. So what that means is if you put in a marker, you can go year after year after year and measure where that is. And using these GPS satellites, you can actually see how fast the plate is moving, which is pretty. So that's just a quick little intro into plate tectonics. As we move through the semester, we'll talk about these a whole lot more. Your job is to make sure you know the 3 different types of boundaries plus those hot spots. You're going to know what happens at each of those types of boundaries and what different types of crust are involved. Plus, you're going to want to know geographic examples of all of them. And I've given you quite a few as we go through, but there's examples all over the globe, and we'll talk in class about some of those.